Today I am going to solve the third assignment of design of reinforced concrete structures. The first question is, consider the following statements concerning with the limit state method of design of reinforced concrete. So he has given two statements, statement 1 and statement 2. Which of the following statements is or incorrect? So many questions will have which of the following statements are correct, but he is asking the incorrect statements. Okay. The maximum strain in concrete at the outermost compression fiber is taken as 0.0035 in bending. So generally maximum strain, so that is epsilon S in concrete, in C, concrete is C, is equal to 0.002 in axial compression, and that is equal to 0.0035 in bending compression. Okay, so the statement 1 is correct statement. Now the maximum strain in tension reinforcement. So the maximum strain in tension reinforcement EST is equal to, generally it is 0.002 plus Fi divided by 1.15 into ES. So here 1.15 is partial safety factor for steel. Okay. So but in the statement he has given it is 0.004. If it is 0.002, the second statement would be correct. Otherwise it is wrong statement. Okay, so second statement is wrong. Answer B for question number 1. Okay, next question. He has given two statements and given some options. For design purpose, the compressive strength of concrete in the structure shall be assumed to be 0.67 divided by 1.5 times characteristic strength. And the second statement is, due to size effect, the characteristic strength of concrete is reduced to 2/3 of its value. The partial safety factor is applied in addition to this. Okay, so generally I'll explain. The characteristic strength can be calculated by 150 mm cubes. Okay, so we will prepare so many number of cubes of size 150 mm to check characteristic strength of concrete. And the dimensions of concrete structures are different and widely varying. So generally the dimensions, practically we are providing columns, beams and all. These dimensions are different. Structures will have different dimensions and variety of dimensions. Okay, so now this entire dimensional effect will be having some effect on the strength of the concrete. So this effect is known as size effect. Clear? Because of this size effect, the concrete strength, initially it is FCK, is reduced to 2/3 of FCK. So that will be 0.67 FCK. Clear? So again to this 0.67 FCK, we will apply partial factor of safety 1.5 for concrete. So you will get it is 0.67 FCK divided by 1.5. You will get it is 0.445 FCK. Clear? So because of size effect, we will reduce the characteristic strength of concrete to 2/3. And again to this, we will apply some partial factor of safety. So partial factor of safety 1.5 for concrete and partial factor of safety 1.15 for steel. Okay, so here statement 1 and 2 both are correct, and because of explanation given by 2, the statement will be 1 correct. Okay, so the answer, both statement 1 and 2 are true. Statement 2 is correct explanation of statement 1. Answer C for question number 2. Clear? Next question. Question number 3. The depth of neutral axis is calculated from known area of steel and is should be. So obviously Generally, we have three types of section: under reinforced section, balanced section, over reinforced section. In under reinforced section, actual depth of neutral axis is less than limiting depth. In the balanced section, actual depth of neutral axis is almost equal to limiting depth. In the over reinforced section, actual depth of neutral axis is greater than limiting depth. Clear? So, actual depth of section, actual depth of neutral axis is less than limiting depth. We call it is under reinforced section. In under reinforced section, steel fails first. As the failure of steel is ductile failure, the complete section will not fail even if the steel has been failed. Okay, so we will adopt this type of section, and in this both steel and concrete fails together. Okay, but in this concrete fails. Concrete is brittle failure. Brittle failure is a sudden failure. Okay, so we will not adopt this. So XA less than or equal to XC, that is less than or equal to limiting value of neutral axis depth, because we will adopt these two sections only. We will not adopt any over reinforced section. Clear? So for question number 3, answer C. Now, which of the following statement is correct? And he has given statements regarding maximum neutral axis depth to the effective depth. So we have formula XU max divided by D is equal to 0.0035 divided by 0.0055 plus Fi divided by 1.15 into S. So in this formula, is there any FCK term? No. That is, the maximum depth of neutral axis to the effective depth ratio will never depend on grade of concrete. Is there any Fi value? Yes, it is there. It is depending upon Fi value. So the answer will be XU max divided by D changes with the grade of steel and independent of grade of weight. So here it is, independent of grade of concrete, independent of grade of concrete, and changes with grade of steel. Okay, so the answer D for question number 4. Coming to question number 5, doubly reinforced concrete section. So generally doubly reinforced concrete section means we will provide steel in the tension side and steel in the compression side. So from here to here, the depth is effective depth. From here to here, this is D dash. Okay, now we have formula stress strain in this range. Strain, maximum strain in concrete at the level of compression steel. Okay, so this is tension steel, bottom steel is a tension steel and top steel is a compression steel. Here the strain will be epsilon SC is equal to 0.0035 into 1 minus D dash by XU. Okay, so it is again one more formula. So the option B for question number 5. Now coming to question number 6, the dimensions of rectangle section is 250 by 350. So it is 250 and it is 350. The clear cover is, and he has provided 3 number of bars, 3 into 5 by 4, 16 square, and the clear cover is 25 and the diameter of the bar is 16. Grade of steel M25 Fe415 bars, and he has given some depth. Effective depth small d is equal to capital D minus clear cover minus diameter by 2. So capital D is equal to how much? 350 minus clear cover is 25. Diameter by 2 is 16 by 2. So it will be 317 mm. So the first statement is correct. Now the second statement is whether he asked about whether the section is under reinforced or over reinforced. So to calculate under reinforced or over reinforced, so depth of neutral axis we need to calculate. XU is equal to 0.87 Fi AST divided by 0.36 FCKB. So that will be 0.87. Fi is 415. AST is he has provided 3 number of 16 mm bars. So 0.36 FCK is 25 into B is 250. It will be 96.79 mm. Okay. So this is XU, actual depth of neutral axis, and XU limiting depth of neutral axis is for FU415 it is 0.480, that is 0.48 into D is equal to 317. So that will be 152. As XU actual less than XU limiting, what type of section it is? Under reinforced section. Clear? So second statement is also correct. And the moment of resistance of the section is, so now moment of resistance of section is equal to 0.87 Fi AST D minus 0.42 XU. Clear? So that is 0.87. Fi is 415. AST is 3 into pi by 4, 16 square into D is 317 minus 0.42 into XU. For under reinforced section we need to take actual depth of neutral axis during calculation of moment of resistance. So that is 96.7. You will get it is 6019 into 10 power 6 Newton mm. So that is approximately 60.19 kilonewton meter. Okay, so the answer will be so statement 3 is wrong. What he is asking, which of the following statements are correct? So both 1 and 2 statements are correct. Answer is A for question number 6. Okay. Now coming to question number 7, he is given some data 250 by 350 mm clear cover, 25 mm tensile reinforcement, the same problem he has given, but he has asked some different options. So now percentage of, we know D is equal to 317. I am not drawing the diagram again, so it is same as earlier diagram. Wait, I'll copy here as well. So you can keep this diagram here. So now small d is equal to 317 mm. So that is we calculated here. Percentage steel provided. So the first option like related to steel, AST by BD into 100. So what is AST? 3 into pi by 4, 16 square by B is equal to 250, D is equal to 317 into 100. So you will get it is 0.76 percentage. Okay, so statement A is correct. And actual depth of neutral axis, earlier problem we calculated it already, 96.79 mm. And lever arm is equal to D minus 0.42 XU. So that is 317.42 XU is equal to 96.79. Approximately you will get 276.34 mm. So the portion of neutral axis 96.7, it is also correct. Statement 2 is correct. And lever arm we calculated 276, but he has given it is 220. So statement C is wrong. And moment of resistance of the section. So moment of resistance of the section due to concrete he has asked, that is limiting moment of resistance. Mu lim is equal to 0.138 FCK BD square. So for FE415 it is 0.138 FCK BD square. 0.138 25 FCK is 25 and B is equal to 250 and D is equal to 317 square. It will be 86.67 kilonewton meter. Clear? So moment of resistance of the section due to concrete is 86.67 kilonewton. So statement D is also correct. Now A, B, D are correct. Only C is wrong. That is only statement 3 is wrong. So the answer is B for question number 7. He has asked not the correct statements. Okay. He has asked the incorrect statements. Clear? And now question number 8. So it is a problem related to T-beam. So the data T-beam is having following dimensions: width of the flange, depth of the flange, width of the web, overall depth of the beam, and M20 grade concrete, Fe415 steel, clear cover 25 mm, and balanced section having, he has given. So you remember this point. So it is a balanced section directly. He himself given balanced section. Balanced section having 20 mm bars. Which of the following statements are correct by using limit state method? So now the neutral axis of the section lies within the flange. So first of all, as he is considered balanced section, as we considering the T-beam as a balanced section and the given steel is Fe415 steel, XU limiting is equal to 0.48 D, that is 0.48 into, from the given data, D is equal to 250 minus clear cover is 25 minus 10. So that is 215. So 215, that it will be 103.2. So this XU limb is less than depth of the flange. That is neutral axis lied within the flange. Clear? If limiting depth of neutral axis is less than the depth of the flange, the section we consider as neutral axis lied within the flange. Whenever the neutral axis lied within the flange, we need to design T-beam as a rectangular beam. So neutral axis lied within the flange and T-beam has to be designed as rectangular beam. Okay, so statement 1 is correct, statement 2 is also correct. So now what he has asked, for a balanced section both compressive force and tensile force is same, right? So equate compressive force is equal to tensile force. Compressive force is equal to 0.36 FCK BF into XU is equal to 0.87 FI AST. So now here AST we can calculate for balanced steel, 0.36 FCK BF into XU divided by 0.87 into Fi. So that is 0.36, FCK is 20, BF is 1000 and XU is 103.2. We calculated this, and 0.87 Fi is 415. So AST is equal to 2057.9 mm. Clear? So 2057, 2058 approximately. This statement is also correct. Now moment of resistance of the given section is, moment of resistance is equal to Mu is equal to 0.36 FCK BF into XU D minus 0.42 XU. So that will be 0.36 FCK is 20 and BF is 1000 and XU is 103.2 and 215 minus 0.42 in 103.2. So it will be 127.54 kilonewton meter. So option D is also correct. So all the statements are correct. So for this the answer is D. So you will have option D here, all. Clear? Okay. And next question. A rectangular beam of width 250 by effective depth 327. So I am drawing here, it is 250. Effective depth D is equal to 327. So M20 grade concrete, Fe415 steel, considering the section to be balanced. Okay. Calculate area of tension reinforcement needed regard to the limit state method. Area of whenever it is a balanced. So first of all we need to take it is limiting depth of neutral axis for Fe415 steel as 0.48 into D. So that is 0.48 into D is 325. You will get it is 156.96 mm. Clear? So now, if section is balanced, so compressive force is equal to tensile force. So compressive force is 0.36 FCK BXU. Tensile force is 0.87 Fy AST. What we want to calculate here, AST is equal to 0.36 20 250 156.96 divided by 0.87 415. Clear? So you will get 782.517 mm square. So the answer for this question is, so option B for question number 9. Okay. Now, last question for the assignment, it is related to doubly reinforced section. Okay. So according to the data, so thoda dhyan rakho isme, it is very important problem in the doubly reinforced section. So he has given data. So let me read the problem. Rectangular beam 300 mm by 400 mm. So first I will draw the diagram. So it is 300 mm and this is 400 mm. The concrete is M20 Fe415 as common, M20 Fe415, and the tensile reinforcement is 420 mm bars. 1, 2, 3, 4. So 420 mm bars, and in the compression side reinforcement provided 216 mm bars. So 216 mm bars in the compression side. The clear cover is 25 mm. So this is 25. Here also it will be 25. This is a clear cover. And the salient points design stress strain curve for Fe415. He has given stress, strain, stress and Newton per mm square. So this all data for what we will use. Okay. So we will see. Now effective depth D is equal to overall depth 400 minus clear cover 25 minus 20 by 2. You will get it is 365 mm. And effective cover for compression steel is equal to clear cover plus half of dia by 2. So that is, you can see in this diagram, this is that I am explaining. This is 25 top portion, remaining is half of the dia. So D dash, you can see here it is D dash. D dash is equal to clear cover 25 plus half diameter, it is 16 by 2. It is 25 plus 8 is equal to 33. So reinforcement on tension side is equal to 4 into pi by 4 20 square. It is 1256.63 mm square. And reinforcement on compression side is equal to 2 into pi by 4 16 square. It will be 402.12 mm square. Okay, first of all, we need to get see here, limiting depth of neutral axis for Fe415 steel 0.48 into D, that is 0.48 into 365, that is will be equal to 175.2 mm. First of all, we need to calculate a limiting moment of resistance 0.138 FCK BD square. So 0.138 FCK is 20, B is 300, D square is 365 square. It is 110.31 kilonewton meter. So this is the limiting moment of resistance. He already given the reinforcement on tension side and reinforcement on compression side. We calculated limiting moment of resistance. Corresponding to this limiting moment of resistance, how much steel will be required? So MU lim, so that is for a balanced section. Limiting moment of resistance means it is a balanced section. So AST required for balanced section. When balanced section means it is AST is equal to 0.36 FCK BXU divided by 0.87 Fy. So that is equal to 0.36 FCK is 20 and B is 300 into XU is 175.2 divided by 0.87 Fy is 415. It will be 1048.14 mm square. Okay, so total tension reinforcement is around 1250, but only 1050 will be for balanced section. Remaining amount will carry some extra moment. So AST extra available is equal to 1256.63 minus 1048.14. So that is equal to 208.49. So this 208.49 area of steel will carry some extra moment. So that moment we need to calculate. So that is additional moment of resistance due to extra steel. Extra tensile reinforcement is MUST2 is equal to 0.87 Fy AST2 into D minus D dash. So that is 0.87 Fy is 415 into 208.49 365 minus 33. So it will be 25 kilonewton meter. Okay, so now check the options that he has given. As per limit state method, the section will take additional moment. So this first statement is correct, right? Okay, now total moment of resistance due to steel. Total moment of resistance due to steel. Earlier it was limiting moment of resistance is 110 and plus 25, that is 110.31 plus 25, that is 135.31. Clear? So this is the total moment taken by steel only in the limiting section as well as in the extra reinforcement. Now we need to calculate the moment of resistance by compression side. To calculate moment of resistance on compression side, first of all we need to calculate strain in the compression steel. To get strain in the compression steel, first of all we need to calculate stress in the compression steel. Clear? So be careful. So we have a formula, I already explained in the objective question. Strain in compression steel is equal to 0.0035 minus 1 minus D dash by XU. So that is equal to 0.0035 1 minus D dash is 33, XU is 175.2. You will have it is 0.00284. In the table, that is the data he has given, corresponding to this strain, what is stress? We need to calculate. So from the data, epsilon SC and FSC values corresponding to 0.00276 strain, the stress value is 351. Corresponding to 0.00380, the stress value is 360. And corresponding to 0.00284, the stress is FSC. I need to calculate this FSC value. This can be calculated by using this equation. This minus this. 0.00380 minus 0.00276. And this minus this. 0.00380 minus 0.00284. Similarly, this minus this. 360 minus 351. This minus this. 360 minus FSC. So if we will calculate FSC value, 359.3 Newton per mm square. Clear? This is the stress at the level of compression steel. Clear? Now, moment of resistance due to compression steel is equal to FSC into ASC D minus D dash. FSC is 359.3 into ASC is, what is the remaining amount of steel? That is compression steel 402.12. It will be 365 minus 33. So that is equal to 47.96 kilonewton meter. So hence moment of resistance due to concrete is same as 110, and compression steel, so that is equal to 110.31 plus 47.96, it will be 158.27. Clear? So in this we will get, as here moment of resistance of the whole section is 158.27, that is moment of resistance of whole section is 110 he has given, this is wrong, and it is governed by steel first. When it is governed by steel first, it is under reinforced section, so this is also wrong. Clear? So options 3 and 4 are wrong. So stresses in steel at the level of compression 359 we calculated, so 3 and 4 are incorrect statements. So you can have options, which of the following statements are correct? When 3 and 4 are wrong, 1 and 2 is correct. Option B for question number 10. Okay, so this is the lengthy problem, so you should concentrate and try to get the concept what I have explained. Okay, thank you.